Hello, and welcome to this presentation on linear regression analysis. Regression analysis is used to draw the line of best fit through coordinates on a graph having the equation y equals mx plus c. That's the equation of the straight line, where c is the intercept with the y-axis and m is the gradient or slope of the line. The line drawn being such that the sum of the deviations of the respective coordinate values from the line is a minimum. Figure 1 shows a positive correlation where the m in the equation y equals mx plus c is a positive value. Figure 2 here shows negative correlation. This line here relates to a negative gradient or negative slope, so the m in the equation y equals mx plus c is negative. Figure 3 shows points plotted that have no correlation. Drawing a linear line through these data would not really be representative of them, so there is no linear correlation here. On applying regression analysis, it's possible to draw two lines of best fit, depending on which variable is chosen as the dependent or the independent variable. For example, if we apply a force P to a component, P shown here applied to the tension specimen, and we measure the extension, called that delta, then P is the independent variable and delta is a dependent variable. And we can write that in the linear form of y equals mx plus c, where in this case delta is equal to m times p plus c, where the x is the p, the applied load, and the y is the delta. And the relationship between them is the linear line. Alternatively, we could apply an extension delta to our component, is shown here, extending the component, and then measure via strain gauge readings, etc., the force induced P. Thus now delta is the independent variable and P is dependent. Again, writing that in the form of y equals mx plus c, that would be P is equal to m delta plus c. So this time delta is on the horizontal axis and P is on the vertical axis, and our line of best fit is again drawn for the two variables. Thus in the top graph of figure 4 here, we can call that a regression of y on x, and in the lower diagram we can call that a regression of x on y, our two lines of best fit. Best fit lines are based on the theory of least squares. We're not going to review this theory in any great detail here, and I would encourage you to look at the references at the end of this video for further information. We're just going to overview the application of the least squares process. So considering the best fit lines we can draw, we can have a regression of y on x or a regression of x on y. We will see that in a moment. So considering figure 5, the regression line of y on x. The regression line of y on x is the best fit line of the form y equals mx plus c. And this occurs when the y values from the line to the coordinate points are at a minimum. So in other words, when the y1 squared plus the y2 squared plus the y3 squared plus the yn squared added up is a minimum for that line, we then have the best fit line and the regression line of y on x. Best fit lines continued here, we're looking at regression of y on x. Equations 1 and 2, shown below without proof, can be used to generate two simultaneous equations from which the constants of m, the gradient of the line, and c, the intercept with the y-axis, can be found. These equations are derived from the least squares theory. Equation 1 is of the form m multiplied by the summation of all the x squared values plus c times the summation of all the x values, and that's equal to the summation of the x multiplied by the y values. That's equation 1. Equation 2 is of the form of m multiplied by the summation of all the x values plus c multiplied by n. That's a number of coordinates, number of points we have in our data set, and that's equal to the summation of all the y values. It's equation 2. Best fit lines continued here. Now we're going to look at regression of x on y. Basically, the line of regression of x on y is simply found by interchanging the x and the y in the equations on the previous slide, in equations 1 and 2. A regression line of x on y is the best fit line of the form x equals to m dash times y plus c dash, and it occurs when the x value squared, so x1 squared plus x2 squared plus x3 squared, etc., added up is a minimum. So we're talking about these values here, the x values. When they are a minimum from the line, we get the best fit line. So figure 6 is a regression line of x on y. Note the constants are denoted here as m dash and c dash, so in equation 3 and 4 we have slightly different notation. So in equation 3 we've got m dash multiplied by the summation of the y value squared plus c dash multiplied by the summation of the y values, and that's equal to the summation of the y times the x values, equation 3. Equation 4 we've got m dash multiplied by the summation of the y values plus c dash multiplied by n, the number of points we're considering, and that's equal to the summation of the x values, equation 4. We will be referring to the equations 1 through to 4 in the following work we're going to look at. So you need to be aware of these equations as they will be used to generate simultaneous equations in the following work. Correlation, usually given the symbol r, which relates to the accuracy of the lines and how close the points are to the lines that have been drawn, is given by the equation shown in the bolded box. So r is equal to, in the numerator here, summation of the x multiplied by the y's, take away n, the number of points we are plotting, multiplied by the x bar, multiplied by the y bar. In the denominator, we've got the square root of, and there's two brackets here, summation of the x squared values, take away n, times the x bar value squared, so one bracket. In the next bracket, we've got summation of the y squared values, take away n times the y bar squared in the second bracket. Note that the square root is across the entire denominator there. So x bar is given as the summation of all the x values divided by the number of them, number of points, and similarly the y bar is the summation of all the y values divided by the number of points. N is the number of points here. If the magnitude of the r value, just its size, forgetting its sense, positive or negative, just its size, is 1, then it means all the points plotted lie on the best fit line. That's perfect correlation. If we have an r value greater than 0.6, that's classified as reasonable correlation. In other words, there will be some discrepancy between the two lines, but it's an acceptable discrepancy. If the r value is considered less than 0.2, that's very poor correlation, or as a student once said to me, naff correlation. So there is limited linear relationship between the points plotted. Figure 7 shows an illustration of what correlation is. Example 1 here. This will provide an illustration of how to apply the 4 equations derived on the previous slides to find the best fit lines to some points given. We're given some data in the question. These will be the 4 points were plotted, and we've got the x and y values for each of the points. We're going to find the regression lines of y on x first of all, and then x on y. So we're going to use a tabular approach to help us structure our solution. First thing we're going to do is work out the x squared value. So this column here, we're going to evaluate the entries. So x squared would be 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. For the y squared column up here, that was simply 1 squared is 1, 2 squared is 4, and 2 squared is 4, and 3 squared is 9. For this middle column here, the xy, that's simply going to be 1 times 1 is 1, 2 times 2 is 4, 3 times 2 is 6, and 4 times 3 is 12. What we do then is summate the values for the x, the y, the x squared, the xy, and the y squared in the final row here. So the first thing we're going to do is determine the regression line of y on x. And we're going to use equations 1 and 2 repeated here for convenience. So for equation 1, we're asked to find m multiplied by the summation of the x squared values. So in this case, summation of the x squared value is 30, so that's 30 times m. Put the number before the symbol here. Plus c times summation of the x values. So summation of the x values here is 10, so that's plus 10 times c. And that's equal to the summation of the products of x times y. So the products of x times y is 23, so that equals to 23. And there's our first equation derived. Equation 2, we've got m multiplied by the summation of the x values. Summation of the x values is 10, so that becomes 10m. Plus c times n, don't forget n in this particular example is 4, so that will become plus 4 times c. And that's equal to the summation of the y value, so that's equal to 8 in this case, summation of the y values. We've now generated our two equations. We're going to solve these equations, these simultaneous equations, using the process of elimination. There are various processes we can use to solve the equations, but I'm using elimination here. So what I've done here is repeat equation 1 from above, and I've multiplied equation 2 above by 3 because I'm trying to make the coefficients, the numbers, of the m values the same. And I do, if I multiply equation 2 by 3, I get 10 times 3 is 30, so 30m, so I get 30m and a 30m. If I multiply the 4c by 3, I get plus the 12c, and if I multiply the 8 by the 3, I get 24. What we can do now is solve the equations by subtracting one from the other. So 30m take away 30m is 0, plus 10c take away 12c is minus 2c, and 23 take away 24 is minus 1. Dividing both sides by minus 2, c is 0.5. Example 1 continued here. We're going to back substitute the value of c from the previous slide into equation 1, again on the previous slide. So 30m plus 10 times c, which was 0.5, we calculated previously, is equal to 23. Rearranging the equation for m, 30m is equal to 23 take away 5, that's a 10 times 0.5, and then divide both sides by 30, m is equal to 18 divided by 30 was equal to 0.6. So therefore our regression line of y on x, y is equal to 0.6x plus 0.5. That's the y equals mx plus c type equation. We're now going to look at the regression line of x on y. So from equations 3 and 4 of our previous slides, just repeated these equations for convenience here. So equation 3, m dash multiplied by the summation of the y squared values. Here's our table, again repeat this from the previous slide for convenience. The y squared value is 18. So I get 18 times m dash plus c dash times summation of the y. Summation of the y from the table is 8. So that's plus 8c dash. and that's equal to the summation of the product of the x times the y, 23, so equal to 23. For equation 4, it's m dash multiplied by the summation of the y values. Again, that's 8, so that's 8m dash. And it's plus c dash times n. N, of course, is 4. There are 4 points we plotted here, so that's plus 4c dash. And that's equal to the summation of the x values. The x value is 10 here, so that's equal to 10. Solving these simultaneous equations, again using elimination. In this case, I'm going to multiply equation 4 by 2 to make the coefficients of the c dash the same. So multiplying equation 4 by 2, I get the 16m dash here, the 2 times the 8, plus the 8c dash, the 2 times the 4 there, is equal to 20, which is the 10 times the 2. Subtracting these equations now, 18m dash take away 16m dash is 2m dash, the 8c dash take away 8c dash obviously 0, and then the 23 take away 20 is 3. Dividing both sides by 2, m dash is 1.5. If we now back substitute the value of m dash into equation 4, I get 8 times the m dash, which is the 1.5, plus 4 times the c dash is equal to 10. Rearranging the equation, I take 12 from both sides, that's the 8 times 1.5 is 12. And then I divide both sides by 4, so I end up with c dash is equal to minus 2 divided by 4, which is minus 0.5. So my regression line for x on y is x equals to 1.5y take away 0.5. Example 1 continued here. We're now going to calculate the correlation, the R value, and again I just repeated this regression table for convenience. Our formula given on the previous slide for R is shown here. It's summation of the xy values, take away n times the x bar times the y bar, that's a numerator, and it's all divided by the square root of, and we've got 2 brackets here, summation of the x squared values, take away n times the x bar squared, in the first bracket there, and the second bracket, summation of the y squared values, take away n times the y bar squared. And don't forget, again, the denominator is all square rooted. To calculate the x bar in this case, it's simply the summation of the x's divided by the number of points here, so that's 10 divided by 4 is 2.5, and to find the y bar, that's the summation of the y values, 8 in this case, divided by the 4 gives us 2. Putting these values into the equation for R, so it becomes 23, summation of the xy values, take away 4, which is the number of points we've got, multiplied by the x bar, multiplied by the y bar. That's a numerator. Denominator, we've got the square root of the summation of the x squared values, that's 30. In this case from our table, take away the n, the 4, times the 2.5, the x bar all squared. First bracket. In the second bracket, we've got summation of the y squared values, which is 18 here. So that's 18, take away the n, 4, times by the y bar, which is 2 all squared. Doing the arithmetic on that, you get 0.95. And just be careful, do not truncate or round up numbers too soon in this calculation, or else you will induce errors and get the wrong value of R. 0.95 is considered a very strong correlation, so these points lie quite closely to the best fit line. Okay, a couple of tutorial exercises now. Exercise 1. In the table below, it shows results of an experiment to establish the relationship between resistance of a conductor R in ohms and its temperature T in degrees C. In the table we're given 6 points. We're given the temperature and the resistance for each of the 6 points. Assuming these data form a straight line, so y equals mx plus c line. Part A, we're asked to find the equation connecting R and T if the type of line is of the form R equals mt plus c. That's an R on T analysis. Part B, we're asked to use the equation in part A to estimate the value of R when T is given as 121.1 degrees C. Part C, we're asked to find the equation connecting t and r if it's of the type t is equal to m dash r plus c dash. That's a regression of t on r. Part D, we're asked to use the equation in Part C to estimate the value of t given that R is equal to 30 ohms, and Part E, we're asked to find the correlation. Exercise 1 continued here. Notice the number of points we're considering in this particular exercise, n is equal to 6, and I'm using my tabular approach here. Also note that t in this particular question is actually the x and r is equal to the y. That's a generic notation of x and y we used when we derive our formulae on previous slides. Again, using this tabular method, I've got my t values given in the question, the temperatures, and I've got my r values, the resistances given. I'm now going to form three other columns of t squared, tr and r squared. T squared is simply the t value, 25 squared is 625, 50 squared is 2500, etc. The tr column would be 25 times 20.7 to give me 517.5, and 50 times 21.6 to give me 1080, etc. And the final column r squared would be the 20.7 squared is 428.49, the 21.6 squared 466.56, etc. And the final row, I've summated all the columns here. We'll be using all these summations in the following analysis. Exercise 1 continued here, Part A. We're asked to find the equation connecting the r and the t. We're told it's of the type r equals mt plus c. So this is a regression of r on t, y on x if you like. We're going to use equation 1, proved previously on a previous slide. In generic terms, that summation of the xy is equal to m times summation of the x squared plus c times summation of the x values. Using the notation of this question, that would be summation of tr is equal to the m times summation of the t squared values plus c times summation of the t values. I've repeated the regression table from the previous slide purely for convenience here. So put in the values, summation of tr in our table, that would be 12,240. The value on the left hand side, that's equal to m times summation of the t squared terms, that's 56,875, so 56,875 m, plus c times summation of t is 525, that's plus 525c. We're going to solve the equations this time using the substitution method. In the previous example we used the elimination method. This time I'm going to use substitution, an alternative method for solving simultaneous equations. Substitution requires us to rearrange one of the equations in terms of one of the variables, and we substitute it into a second equation. So looking at the equation above here, I'm going to rearrange this for c. To do this, to get c as a subject, I have to take 56,875 m from both sides of the equation, and then I have to divide throughout by 525 to give me c as a subject. Doing the arithmetic on this, I get c is equal to 23.3143, take away 108.3 recurring m. I've called that equation 1 here. Notice that's a Roman numeral 1. Now we're going to use equation 2, proved previously, and that was generically summation of y is equal to m times summation of x plus c times n. Using the notation from this question, that summation of r is equal to m times summation of t plus c times n. And again, taking the information from the table on the right hand side, summation of r is 136 on the left hand side, and that's equal to the m times summation of t. Summation of t is 525, so 525m, plus number of points in this case n is 6, so that's 6 times c. And that's called equation 2 in Roman numerals. Exercise 1 continued here, still looking at the regression line of r on t. I've repeated equation 1 in Roman numerals from the previous slide. What we're going to do now is substitute equation 1 into equation 2. Notice those are Roman numeral equations. So 136 is equal to 525m plus 6 times, and this is where I put the c value into the equation. That is the value of c, the expression for c there, equation 1. If I now multiply out the bracket, I will get an equation of 136 equals to 525m plus 6 times 23.3143 is 139.8858, and 6 times minus 108.3 recurring is minus 650m. If I bring my like terms together on the right hand side, I get 520m take away 650m, that's minus 125m, and if I take 139.8858 from both sides, on the left hand side I now get minus 3.8858. Dividing both sides by minus 125, I get the m is equal to 3.8858 divided by 125. Notice the negatives on both sides cancel there. That gives me a value of m of 0.0311 ohms per degree C using the units in this particular problem. If I now back substitute the value of m into equation 1, the Roman numeral equation 1, above here, I get C is equal to 23.3143 take away the 108.3 recurring multiplied by the m, which from above is 0.0311. If you do the arithmetic on that, C is equal to 19.945 ohms. That gives us now our linear regression equation of R on T. So R is equal to MT plus C, put the numerical values in, I get R is equal to 0.0311T plus 19.945. And I've called that equation 3 in Roman numerals. Exercise 1 continued here. I just repeated the expression for R from the previous slide, the 0.0311T plus 19.945. That was equation 3 in Roman numerals. Part B now wants us to use this equation to estimate the value of R given that T is equal to 121.1 degrees C. So from the equation 3 above, R is equal to the 0.0311 multiplied by the 121.1 and then add the 19.945. So R is 23.7 ohms. Exercise 1 continued, part C. We're now asked to find the equation connecting T and R, so regression of T on R, if the equation is of the type T is equal to m dash R plus C dash. We're going to use equation 3 derived at the beginning of this presentation, and generically that is summation of yx is equal to m dash times summation of y squared plus c dash times summation of y. Using the notation in this question, that summation of rt is equal to m dash multiplied by summation of r squared plus c dash times summation of r. Again, I've repeated the regression table for convenience on this slide. To put in the values, r times t is 12,240, so on the left side I get 12,240, and that's equal to the m dash times summation of r squared. R squared is 3,093.26, so that 3,093.26 m dash plus summation of the r in this case is the 136, so that's plus 136 c dash. Again, I'm going to solve the equations using substitution, so I need to rearrange one of the equations in terms of a variable. I'm going to rearrange the above equation in terms of c dash. To do that, I have to take the 3,093.26 m dash from both sides and divide both sides by 136. Doing the arithmetic on that, c dash is 90, that's the 12,240 divided by 136, take away 22.7446 m dash, that's the 3,093.26 divided by 136. I've called that equation 1, again using capital Roman numerals here. Equation 4, derived at the beginning of the presentation, is summation of x is equal to the m dash times summation of y plus c dash times n. Using notation for this question, that is summation of t is equal to m dash times summation of r plus c dash times n. Again, from the table on the right hand side, summation of t in our table is 525, and that's equal to the summation of r is 136, so 136m dash plus 6, that's the number of coordinate points we have, times c dash. I've called that equation 2 in the capital Roman numerals there. Exercise 1 continued here. I just repeated these equations from the previous slide. We're now going to substitute equation 1 above into equation 2. These are the Roman numeral equations. So 525 is equal to 136m dash plus 6 times c dash, and c dash is this expression. So there's my 90 minus 22.7446m dash. If I expand the right hand side, I will get 6 times 90 is plus 540, and 6 times the minus 22.7446m dash is minus 136.4676m dash. Bringing the like terms together on the right hand side, I get 136m dash take away 136.4676m dash, which gives me the minus 0.4676m dash on the right hand side here, and then taking 540 from both sides gives me minus 15 on the left hand side. Simply dividing both sides by the 0.4676 and ignoring the negatives because they cancel on either side, m dash is equal to 32.08 degrees C per ohm. If I now back substitute the value of m dash into the equation 1 above here, this equation, I get c dash is equal to 90 take away 22.7446 times by the m dash value of 32.08. That gives me a c dash value of minus 640 degrees C. Thus our linear regression equation for t on r, t is equal to m dash r plus c dash, can be written as t is equal to 32.08 r take away 640. And I've called that equation 3 in the Roman numerals. Exercise 1 continued here, just repeated this equation from the previous slide. We're now looking at part D. We've got to estimate the value of t given an r is equal to 30 ohms. So from the above equation, t is equal to 32.08 times the 30 take away 640 gives us a value of temperature of 322 degrees C. Okay, exercise 1 here continued. This is part E. We're asked to now find the correlation R. Just repeated the regression analysis table for convenience here. And don't forget the number of points we're considering is 6. There are 6 points in our table that we plotted. Also note that in this case the T, the temperature, is actually equal to X in generic terms, and the R resistance equal to Y in generic terms. We're using the T and R because that was given in the question, but the formulae here are in terms of generic X and Y. So in this case, to find the X bar, which is really the T bar, it's summation of X over the N. In this case, the summation of X is the summation of T here, which is 525 divided by N, which is 6. So our X bar is 87.5 degrees C, and then the Y bar, which is really the resistance in this case, is the summation of Y over the N. Summation of Y in this case is summation of R, so that's 136 divided by N, 6. That gives me a Y bar value of 22.6 recurring ohms. Now using the equation for correlation R, we derived from the previous slide. Don't forget that summation of the X times the Y terms, take away N, number of points, times the X bar times the Y bar from above. That's all divided by the square root of, in the first bracket, summation of the X squared terms, take away N times X bar squared, and in the second bracket, summation of the Y squared terms, take away N times the Y bar squared. Don't forget the whole denominator here is square rooted. So putting the values into the equation for R, from our table, summation of the XY terms, in this case that will be the 12,240, summation of TR in this case, so 12,240, take away 6, the number of points, times by the X bar, times by the Y bar from above. That's all divided by the square root of summation of the X squared terms, in this case that's summation of the t squared terms, so that's 56,875, take away the n multiplied by the x bar squared. In the second bracket we've got the summation of the y squared terms, that's the summation of the r squared in this case, so that's 3093.26, take away the n, 6, multiplied by the y bar squared. If you do the arithmetic on that, r evaluates to 0.9988. Again, I would encourage you not to truncate your numbers too soon or round up your numbers too soon when evaluating the correlation r, as if you do, you will induce errors in the final value of r. Our correlation of r of 0.9988 is a very good correlation between the t and the r values in this particular question. Exercise 1 continues, part E. I'm just showing this for reference. This is an alternative method for finding correlation. I'm not suggesting you use this method, but I know that students in the past have gone away and researched their own formulas, and they've come up with this formula for correlation. Now, what I must emphasize, it's a different formula for R than the one we have been using, and it requires a different table to be constructed. The problem I find is students find this formula on the internet or in a book, but they use the information from the previous table that we've been using. But you cannot use that information with this formula. You must use the table with the headings shown here to use this equation. If you do construct this table and you use the formula, you'll get exactly the same value of R that we have found on the previous slide. But it is a different method. I'm just showing this for reference. So be very careful. If you pick up this formula, you need to construct a new table. Exercise 1 here just shows some graphical plots of the information on the previous slide. This is a plot of the R on T. This is having T on the horizontal axis and R on the vertical axis, and it shows the best fit line through the points and how accurate it is. There's the equation R is equal to 0.0311T plus the 19.947, which you notice we calculated in our work on the previous slides. This particular computer package gave an R squared value in its output of 0.9977. If you square root that, you will get our particular R value calculated on the previous slide. Exercise 1 continued here. We've got now a plot of the T on R diagram, temperature on resistance. We've got resistance on the horizontal axis and temperature on the vertical axis here, and we've got our best fit line drawn through the points. The equation of the line given by this computer package is T is equal to 32.096 R take away 640, which is what we calculated on our previous slides, and again it's given us an R squared value 0.9977, but if you square root both sides, so you'll get 0.9988 as we did in our calculation. Okay, we'll leave you with exercise 2 to attempt. Descriptive question again, you need to extract the information of the question, but it follows a very similar process to example 1 and exercise 1. So I will leave you with parts A, B, C, D and E to attempt. The answers to those parts are given at the bottom of the slide. Full solution is shown on the following slides, but I would encourage you to stop the video here and attempt this question in full using the example and the exercises we previously looked at as the basis of your solution here. So here's the solution for exercise 2. This is our table of information we're generating. Don't forget the n in this case is 7. We have 7 points in the data series we're looking at, and we need to generate the columns of f squared, f times delta, and delta squared. So these values at the bottom of the page, you'll be using these in all your work that follows over the following slides. Exercise 2 continued is part A solution, generating 2 equations here. Exercise 2 part A continued here, finding the values of M and the values of C. Finally we end up with our full equation for regression of the delta on f, or the y on x. Exercise 2 continued. This is part B, where we're using the equation from the previous page, and we're putting the value, in this case, of 60 newtons to work out the value of the extension. This compares reasonably well with the actual value if you look at the information given to us. Exercise 2 part C continued here. Exercise 2 part C continued again, ending up with the values of the m dash, the c dash, and again the equation here. Exercise 2 continued, repeated this equation from the previous slide. We're doing part D here. We're estimating the value of f given the value of delta. So from the above equation, put that value into the equation. Gives a value of 60.72 newtons. Again, if you compare that to the actual test results, it's about a 1.2% error. And exercise 2 part E, determine the correlation R. Very good correlation value. Exercise 2 continued here. This is a plot of the extension against the force. So this is extension on the force. Best fit lines for the points. Our equation of the line, our squared value. Exercise 2 continued here. This is another plot here of force against extension. Force on extension. And the best fit line through the points. Equation, r squared value. And I'll leave you with some tutorial questions. Again, I would strongly encourage you to attempt these questions. The answers are given in the square brackets adjacent to each question. Question 1 and question 2. Question 3, and again the answers are given in the brackets. Here's the bibliography used to develop the presentation. I would strongly encourage you to review these reference sources. Very good reference sources here that will have background information and more theory about how the least squares approach is used. I hope this has been of interest to you, and thank you for viewing.